Intime supports several APIs that ease implementing your application. This chapter explains low-level functions for fine-grained access to certain kernel objects. Timers are discussed and how periodic execution of functions can be controlled. Working with the various types of interrupts concludes this chapter. There are situations where more control over scheduling or less error checking may be necessary. Intime provides low-level functions that form a less protected subset of the normal kernel functions. The low-level functions cover time management, mailboxes/semaphores and locking the thread scheduling. In general, the low-level functions should be considered as a tool for the implementers of the Intime kernel. There are cases where low-level functions may be useful for the RT programmer. When the handler, thread model for interrupt processing is too restrictive, an interrupt handler may use low-level semaphores/mailboxes and other low-level functions. For an example, let the Intime application wizard generate an interrupt handler using a low-level semaphore/mailbox. The other case to use low-level objects is when the limit on the number of objects becomes a problem. 8K is the limit for regular objects, but there is no limit on low-level objects. Before applying any low-level function, make sure that there is no regular alternative. Be aware that there is no error checking on parameters to low-level functions, such as the type of an object, or the size of a structure. Low-level functions are identified by the prefix kn, e.g. kn create semaphore, versus create semaphore for normal semaphore. Kn stop RT scheduler temporarily locks the scheduling mechanism or places an additional lock on the mechanism for the running thread. Any thread state transitions that move the thread from the running state to the ready state are delayed until scheduling is resumed. For example, with scheduling stopped, if the running thread sends a message to a mailbox at which a better priority thread is waiting, that waiting thread becomes ready, but it does not become the running thread until scheduling resumes. You can invoke this function repeatedly. Scheduling is resumed only when all scheduling locks are cancelled. This call is non-scheduling and is safe for use by interrupt handlers. Kn start RT scheduler cancels one scheduling lock imposed by the Kn stop RT scheduler function. If the lock that is cancelled is the last outstanding scheduling lock, all thread state transitions that were temporarily delayed are carried out, and the best priority ready thread begins executing. This is a scheduling call and can be used in an interrupt handler after signal end of RT interrupt has been called. Kn create RT semaphore creates a low-level semaphore with 0 or 1 initial units. Flags can be one of kn_FIFO queuing, kn_priority queuing, or kn_region, implies priority adjustment, ORed with one of kn_0 units or kn_1 unit. Kn delete RT semaphore deletes a low-level semaphore. All threads waiting at the semaphore are awakened with the e_non-exist exception code. Kn wait for RT semaphore waits for a unit from the specified low-level semaphore. Kn release RT semaphore releases a single unit to a specified semaphore. If threads are waiting at the semaphore, the thread at the head of the queue is awakened and given the unit. Note, this call may trigger scheduling another thread. Call Kn stop RT scheduler in interrupt handlers before using this call. Warning, there is no protection against deleting a thread holding a low-level region. Kn create RT mailbox creates a low-level mailbox with the given specifications. Size must be Kn_mailbox_size plus, CB message size and Kn_mailbox_message_overhead, DWQ length. Optionally a slot can be reserved for a single priority message. Kn delete RT mailbox deletes the low-level mailbox associated with the given kernel handle. All threads waiting at the mailbox are awakened and given an e_non-exist exception code, and all messages queued at the mailbox are lost. After this call, the memory assigned to the mailbox is available for reuse. Kn send RT data sends a data message to the given low-level mailbox. This fails if the mailbox queue is full. Kn send RT priority data sends high priority data to a low-level mailbox, bypassing the queue. There is only space for one high priority message in the mailbox, so, if this is full, an error status results. Note that there is no equivalent for normal objects. KN wait for RT data requests a message from a specific mailbox. If a high priority message is present, that is the message returned, otherwise the message at the head of the queue is returned. If no message is present, the calling thread is put to sleep for the number of low-level TEECs specified. KN get kernel time returns the current value of the 64-bit counter that the kernel uses to keep track of the number of low-level clock ticks that have occurred. When the kernel is initialized, the count is set to 0. The period of a low-level clock tick is configurable and the current configuration may be read using copy RT system info. Although this call is non-scheduling, it is not recommended for use by interrupt handlers. KN set kernel time sets the value of the counter that the kernel uses to keep track of the number of clock ticks that have occurred. Although this call is non-scheduling, it is not recommended for interrupt handlers. More precise measurements. The EEN-time timestamp counter allows even more precise time measurement. The timestamp counter is a facility which is accessible from all nodes, and also Windows via NTX. The best possible source is automatically configured in order to provide a counter which is coordinated between the different nodes. The sources run at exactly the same frequency, and also if possible synchronized, in other words returns the same value from each node at a given instant. Where possible the source used is the system HPET, High Precision Event Timer. A feature of many PC chipsets providing a 64-bit counter and programmable timer feature, but if the HPET is not available the CPU timestamp counter, TSC, is used. Timers allow threads to run periodically at predetermined intervals. Timer interrupts can be simulated using alarms. When using timers, there are these issues to be addressed. RT sleep, and also KN RT sleep we will see on the next page, starts counting down ticks only when it is called. If you need to execute some function at a fixed interval, you should subtract the function time from the interval to get the actual sleep time. If this is not feasible, you can use a low-level alarm which counts independent of the thread it wakes up. The tick length of 10 milliseconds is too long, there is a low-level timer that counts at a fraction of that. The fraction can be configured, by default it is 500 microseconds. The timers run at fixed intervals, so for example it is not possible to wait for a given time starting in the middle of a tick. If the low-level tick does not help by its higher resolution, the only solution is to add hardware that can be programmed to provide an interrupt after the required time. An alarm is an EEN-time object which is signaled when a given time interval has expired. The alarm mode may be single shot or repeatable, CDW alarm flags. The differences between an alarm and the RT sleep function are: RT sleep operates in units of 10 milliseconds, the alarm unit is the low-level tick, default 500 microseconds. RT sleep starts to count when the call is executed, an alarm continues counting while the thread may be running. Note that any existing alarm objects are deleted automatically at process end. An EEN-time communication object signals an internal or software event, but almost every real-time system has to work with some hardware events. Such hardware events are usually signaled to the processor by means of an interrupt. In this chapter we discuss what interrupt processing features are provided by EEN-time. The original PC used 18259A programmable interrupt control, PIC, later a second one was added. These days, the exact chips are no longer used, but more or less the same functionality is implemented in chipsets and /or APICs. For our discussion here the difference between a PIC and an APIC is not relevant. By default, the EEN-time software takes over the system clock, IRQ0, and, in the EEN-time for Windows configuration, multiplexes the clock interrupt between the RT and the Windows kernels. RT applications can take over other interrupts, but must ensure that Windows drivers do not try to use the associated devices, such as the keyboard, mouse, etc. When an interrupt occurs and no interrupt is being processed yet, an interrupt vector is determined, the current processor context, CSEIP, flags, is saved on the current stack and the address of the next instruction is extracted from the interrupt descriptor table, IDT, at the same time the interrupt flag is set. That flag and the processor context are restored when the interrupt handler returns with an IRET instruction. Here is an example of the code for an interrupt handler. Since Visual Studio has no option to generate interrupt handler code, this must be done by _ASM statements, and the _DECLSPEC, naked, control. To get an idea of the required prologue and epilogue, let the InTime application wizard generate an interrupt handler for you, and read the code and comments. An interrupt handler does not execute in the same context as an InTime thread, instead it runs in ring 0, i.e. less protection, and has all interrupts disabled. You cannot debug an interrupt handler with Spyder or Visual Studio, but must use SDM with a separate terminal, can use the emulation of an external terminal by the PC console. To make coding an interrupt handler a bit easier, the include files contain a number of macro definitions, __interrupt, __interrupt, _prologue, _interrupt return, _shared interrupt prologue, shared interrupt return. See the include and help files for details. The setRT interrupt handler system call is used to establish an entry in the interrupt descriptor table. The source of the interrupt must be identified when setting up an interrupt handler so InTime knows into which IDT slot to install the handler address. This is specified by the W-level parameter. For legacy-style interrupts, using a PCI, W-level can be IRQ0_level to IRQ15_level. For PCI-based systems using MSI, W-level is determined by scanning the hardware of the system, discussed later in this chapter. The ByMaxInt parameter specifies the relation between the interrupt handler and its interrupt thread. 0. No interrupt thread, the handler is on its own. 1. The current thread becomes interrupt thread, when the thread is processing an interrupt signal, the interrupt is disabled. Greater than 1, the current thread becomes an interrupt thread, when the thread is processing an interrupt signal. The interrupt remains enabled until there are as many signals pending as this value. Use the resetRT interrupt handler system call to remove a handler from the IDT and disable the interrupt level. An interrupt thread waits for a signal from its interrupt handler by the wait for RT interrupt function. Enter RT interrupt is required at the start of a handler to set up addressing for its data area. Its parameter may not be a global variable, so it must be a constant or the result of get RT interrupt level. Before an interrupt handler returns, it must call either signal RT interrupt thread, if there is an interrupt thread, and it should be signaled, or signal end of RT interrupt, if there is no interrupt thread, or the thread needs not be signaled. Enable RT interrupt and disable RT interrupt can be called from an interrupt handler, and also from any RT thread, to enable/disable the interrupt level permanently. Besides the functions mentioned here, and some low-level functions discussed later in this chapter, an interrupt handler must not call any InTime functions. In addition, an interrupt handler should not use any floating point operations. Warning: inside the handler you should never use the address of an automatic variable, nor should you call a function, directly or indirectly, that uses the address of an automatic variable, because an interrupt handler runs in ring 0, the normal setup of data area and stack is different. The second parameter in setRT interrupt handler specifies the maximum number of outstanding interrupt signals that can be queued before InTime disables that interrupt level. The call to wait for RT interrupt enables the level when the number of outstanding interrupt signals is less than the specified maximum. The setRT interrupt handler call does not enable the interrupt level when the ByMaxInt parameter is greater than 0. This occurs when the wait for RT interrupt is executed the first time. EanTime provides a number of alternatives that a programmer may choose from. Handler only. This is rather uncommon, as the handler is not allowed to execute any EanTime functions, with a few exceptions related to interrupt handling. Handler and interrupt thread. This is the most common choice, as it allows the programmer to distribute the work between the handler, most time-critical actions, but no EanTime functions, and the thread, less time-critical, normal EanTime environment with thread priority bound to interrupt level. Handler with service thread and low-level mailbox or semaphore. When an interrupt must be processed by more than one thread, the fixed handler thread model can be too restrictive. Instead, the EanTime kernel offers some low-level functions that allow a handler to use low-level mailboxes and semaphores to trigger service threads. We recommend you have the EanTime wizards in Visual Studio create respective sources. Just add your specific logic according to your application. With legacy boards, ISA and early PCI specs, all interrupts are disabled during the execution of an interrupt handler. More current boards, with PCIe, MSI capabilities, do not disable interrupts but also don't latch interrupts, so they may be missed if not processed in time. Therefore, an interrupt handler should execute quickly so other interrupts are not missed. If the servicing of an interrupt is a time-consuming activity, it should be split between an interrupt handler and a thread. There are two common alternatives to implement the thread. As an interrupt thread, a concept built into EanTime that connects an interrupt handler with its interrupt thread and also does all cleanup on exit. As a service thread, the system designer is free to implement any sort of handler thread interface as long as it uses low-level functions only. In this scenario, a low-level semaphore or mailbox is used by the interrupt handler to trigger an ordinary thread taking care about the time-consuming activities. To use a thread to service the time-consuming activities for the interrupt handler needs to carefully control thread scheduling by use of KNStop-RT scheduler and KNStart-RT scheduler. This scenario also requires the application to do all cleanup like disabling the interrupt level it used. The interrupt thread does not have to be activated with every interrupt. The interrupt handler can decide when to invoke signal end of RT interrupt versus signal RT interrupt thread. The diagram shows the design for receiving commands from a serial terminal, where a command is ended with a CR character. The interrupt thread needs to run only when a complete command has been received. While the interrupt thread runs, the state of the interrupt depends on the ByMaxInt parameter, which must have been non-zero since we have an interrupt thread. If ByMaxInt is 1, the interrupt is disabled while the interrupt thread runs. We could miss interrupts if processing the command takes too long. If ByMaxInt is greater than 1, the next command can be entered while the current command is processed. There must be more than one buffer. The value of ByMaxInt determines how many buffers must be present and how many commands can be entered ahead. Handler and thread need to maintain an index for the command buffer to use, and each cycles its own counter. The interrupt handler/thread model was designed as a simple, efficient way to deal with interrupts that may or may not need attention from a RT thread. But there may be cases where an interrupt needs to be processed by more than one thread, or where the fixed priority assignment of interrupt threads is a problem. In these cases, low-level features may be used. Instead of having a fixed interrupt thread and using signal RT interrupt thread, we now only install an interrupt handler. The interrupt handler may send one or more messages to low-level mailboxes and or may release units to low-level semaphores. To avoid locking up the interrupt by thread switching away from the handler, this must be done in a well-defined order in the interrupt handler. Enter RT interrupt, level. KNStop-RT scheduler. KNSend-RT data, LLMBX, test, 4. Signal end of RT interrupt, level. KNStart-RT scheduler. / return from handler. If you do not adhere to this rule, the system may crash. You may only use low-level objects, no ordinary mailboxes, etc. The wizard can generate sample code for doing a single send message or release unit from the interrupt handler. This code can easily be extended. When the interrupt originates from a PCI device, the level is not fixed in the hardware but is configured at PC setup time. To be able to handle such interrupts with flexibility, EENTime includes a PCI support library, PCIBus.lib, with a number of functions, see PCIBus.h. An example is the function PCI find device shown on this page. Given a vendor and device ID number, it returns information including the belonging interrupt level. For details see the help file. Note that the EENTime RT process wizard can generate PCI interrupt handling code. We strongly recommend to use the wizard. The returned interrupt level, DEV by int line, then is used as part of the parameter W level in the interrupt-related function, slightly different for shared and message signaled interrupts. Note, when a PCI device is installed in the system, Windows will detect it and install a device driver for it. To allow EENTime to use such a device, it must be passed to EENTime using the EENTime Device Manager. In some PCs, a single hardware interrupt line is shared with multiple interrupt sources. When such a line signals an interrupt, all connected handlers must be executed to probe their device. EENTime allows interrupt sharing only if all handlers are on the RT side. Windows itself allows interrupt sharing if all handlers are in Windows, so a single interrupt line cannot be shared between Windows and RT. To set up shared interrupt handling, the handler must be installed using the setRTInterruptHandlerEX function. When a shared interrupt occurs, each handler is called from a system handler. The EENTime application wizard can generate the necessary code for sharing interrupts. Example for setting an interrupt handler for shared interrupts of PCI devices. See slide PCI interrupts, for details on how to use the PCI library. For PCI and MSI interrupts, use setRTInterruptHandlerEX to set the interrupt handler. The first three parameters are identical to the function setRTInterruptHandler, see respective slide further up. For shared PCI interrupts, the parameter W level is generated by respective calls to the PCI library, see slide PCI interrupts, and ORed with shared _level. There is one additional parameter that varies for shared versus MSI interrupts. For shared interrupts, LP_param block is a pointer to a user-defined parameter block for this handler. setRTInterruptHandlerEX returns a 16 bits reference identifying this particular handler. The reference actually is a modified interrupt level that identifies the specific handler to EENTime. In modern PCs you find PCIe cards that are capable of using MSI. MSI directly generates interrupt vectors. If your device supports MSI, then you can tell the RT kernel to use this feature to invoke your interrupt handler. Some devices can generate multiple interrupt vectors to signal different conditions or else to signal different cores. Multiple MSI support is available in EENTime. MSI handlers are never shared, since each MSI event generates a different interrupt vector. This has two advantages. The performance is slightly better than a shared handler because only one is called, and the device is isolated from any other interrupt source. Setting up an interrupt handler for a MSI-capable device requires initialization of the PCI dev structures, see slide on PCI interrupts, plus MSI-specific settings shown in above example. The handler then has the same API as for shared interrupts. For PCI and MSI interrupts, use setRTInterruptHandlerEX to set the interrupt handler. The first three parameters are identical to the function setRTInterruptHandler, see respective slide further up. For message signaled interrupts, set W level to MSI_level. There is one additional parameter that varies for shared versus MSI interrupts. For MSI interrupts, the fourth parameter must point to an initialized MSI_param or MSI_param_EX structure. This structure then has a pointer to a parameter block that is passed into the interrupt handler with every call. setRTInterruptHandlerEX returns a 16 bits reference identifying this particular handler. The reference actually is a modified interrupt level that identifies the specific handler to eentime. The reference returned by setRT interrupt handler EX and the pointer to the respective parameter block is passed to the interrupt handler as a parameter. Use the eentime application wizard to generate the necessary code for shared interrupts and MSI interrupts.